Continuing our look at arithmetic operations and MIPS and how they're handled, we're going to look at multiplication this week. Today we're just going to have a look at binary multiplication and how we do that, and the next videos we'll be having a look at how MIPS handles that. Before we get going, remember that unsigned addition is the same as signed addition. Remember that we can increment and decrement signed and unsigned numbers in the same way. All we have to be wary of is their meaning and where they wrap around. And particularly for overflow, because that can cause us no end of issues. Now, one thing that's always a very handy thing to know is that multiplication is simply repeated addition. So we can think of 3 times a as being a plus a plus a. Now, what does this mean? Well, this means that unsigned multiplication is the same as signed multiplication. So because we have that coming over from addition, we can carry it forward into multiplication. Well, let's see, how would we do multiplication with binary by hand? Well, let's have a look. We have two numbers here, 43 and 37, and we're going to multiply them together. So what do? Well, we do it bit by bit, and we keep in our heads the idea that one bit times another bit is either going to be 0 or it's going to be the multiplication. So if we have a 0 in a column, we can just safely say that's not going to add anything to our multiplication, and when it's a 1, we need to be wary of that, and we handle that by shifting. Now, what does that mean in practice? Well, let's see. So we start at the least significant bit, and that's a 1. So we get a copy of the number above, and we copy it down. Next, we have a 0 in the next place column, but that's in the new place value. So if there was a value there, that would be 2 to the power 1. It's the 2's column. So we would get more than just 1 times that number. So we need to shift it along to represent the difference between the place values. But we get a 0 there because 0 times any number is always going to be 0. Next, we have a 1 in the 2 to the power 2 column, so the 4's column. So we shift along and copy down. I hope this is becoming clear to you, the pattern we're going to have to repeat here. But next we have a 0, so we shift it along and we copy 0 down. In the next column, it's the same again, a 0, so we just copy a 0 down. And then the most significant bit column, we have a 1, so we copy the number down but shift it along. And that's us most of the way there. So what do we do next? Well, we get rid of the zeros and we add these together, which gives us 1591 in binary. So that's how we carry it out. But why is this important? Well, it's important because we can do multiplication by shifting and adding. That's what we did there. All we did was shift along and add. Now, why is that good? Well, it's good because multiplication is very expensive in comparison to adding. So if we can capture multiplication by doing shifting and then adding, that's going to be much quicker for us, and it's going to lead to some real efficiencies. So that's something we've covered before, but we've never really covered it in much detail, but that's why we're interested in shifting so much and why I keep telling you to do it. So with that in mind, here's some key information to keep in your head. The product of two 32-bit integers, or words, requires 64 bits. The product of two 16-bit integers requires 32 bits, and the product of 2 bytes requires 16 bits, or 2 bytes. To generalize this, the product of an n-bit and an m-bit integers requires n plus m bits. Okay, so let's have a look at sign extension. So we've had a look at sign extension before, particularly with loading half words, loading bytes and stuff like that, so that we capture the meaning of a word or a value properly. Now, this is very important with multiplication because, well, let's look at this example, 5 times minus 4. So we have a value of 5 at the top there, so 1 in the 4's and a 1 in the 1's column. And then we have minus 4, but minus 4, if you knew it was unsigned, you would recognize that that's minus 8 plus 4, so you get 4 out. If you didn't realize that was minus 4, you would think that's 12. So what happens is, when we do the multiplication, now this is just shifting along, we're missing out the zeros, so we'd have a 0 in the 1's column, down here, and then a 0 in the 2's column, and this is in the 3's column, or the 4's column. We actually get a copy of the number, so these zeros are just representing the shifting along, and we're missing out the overall zeros, these values here when multiplied, just giving a 0. So we're missing that out for the sake of speed, and say that and then spent 30 seconds explaining it. But what this gives us at the end is 60, so this is reading the meaning as 5 times 12, not 5 times minus 4. So something has clearly gone wrong here, and that's because we need to do sign extension before multiplication. So let's have a look at that. So we know that these are two 4-bit words, or values, sorry. So we're going to need 8 bits overall to represent them. So we extend this negative number to the left with 1s for 4 bits so that we have enough space to capture the multiplication. And then we just carry it out as before, and you can see this shifting along here with inserting zeros in the places to represent the shifting and the multiplication. And this gives us at the end minus 20. So you need to be wary of when you're doing your sign extension and when you should do it, in particular with multiplication, because it will have a very different meaning if you don't. So this is how we do it properly, is to extend it before you do the multiplication. But that's everything I want to cover here today. In the next video we're going to have a look at multiplication in MIPS and how MIPS handles it. But I hope you found this useful. If you have any questions about anything I've covered here today, please do let me know. Thanks.